Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. All math-based, of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Stepping aside as we get our last video for Chapter 8 on Similarity for the Big Ideas Math Integrated Math 2 textbook. Now, this is not something out of the Big Ideas Math Integrated Math 2 textbook, but it features those things from those chapters, sections 8.1 to 8.6. This is another Are You Ready packet made from my highly esteemed colleague, and I'm going to do a solution guide video for y'all. If you'd like to download this thing, check out the PDF down below in the description section. You can also check out timestamps for each individual problem that I do. I'll just whip through it as I see it. Haven't done the problems yet, so your guess is as good as mine if these are set right. Let's go and give them a shot right now. Are you ready? Chapter 8, Similarity. We're going to start with lesson 8.1 on dilations. Now, dilations can be shown on graphs or not. You could even use compass construction for these things. I doubt we're going to use that here, but we'll see what we got. Find the scale factor of the dilation, then tell whether the dilation is a reduction or an enlargement. Now, what we see is, and hopefully you see the color on it if you printed it out black and white, there's blue and there's red. The red is the image, the blue is the pre-image, the one before dilation. The reason I know that is because P versus P prime. P prime meaning the transformed version of, say, point P. C is the center of dilation. Don't look at this as like a big like glass object like thing. There's two triangles and these lines that are showing the extension out from here. We got a distance from C to P of 5 and C to P prime of 10. The scale factor is how much you enlarge or reduce it, but how many times you multiply it by to enlarge or reduce it. Scale factor here, you divide CP prime divided by CP, those distances. We're going to do 10 divided by 5 and get 2. 2 is what you would have to multiply by to go from 5 to 10 to enlarge this object. And so here's the thing about the 2. 2 is not only the distance from center C, but it's also how much bigger this object got. This got twice as big here, this got twice as big here, and this got twice as big here. And these distances all got doubled. Reduction or enlargement, this is an enlargement. It's also one of those things where it's like, which one would you like to answer first kind of thing? Because then you also know which way to divide. If you can tell that it got bigger, maybe answer that first and say, this number's got to be more than 1. If it was a reduction, your number would be less than 1, meaning like 1/2 or something. It would be between 1 and 0. Number 2, graph the polygon and its image after a dilation with scale factor K. We have B, C, and D with this scale factor here, so we're going to make a triangle out of it. Now this is at 15. Okay, good. This graph goes up this much. Hopefully you can see these numbers at least enough to be able to plot these points. Let's go B at negative, this is kind of hard to see, -5, -10, I believe is right there. Sorry if I messed that up a little bit. C is at negative, 1, 2, 3, 4, 5, 6. Okay, that one's the 10. -10, comma 15. Oh, it's big. But we're going to reduce it a lot, right? Scale factor of negative, doesn't matter negative, but the 1/5. It's going to be 5 times smaller than it was. D is at 0.5. Okay, here's the original triangle. I'll let you draw it, or you can pause while I connect these. We're going to reduce this thing. We're going to make it 5 times smaller, 5 times closer to the origin, but it also flips on the other side of the origin. This negative thing is going to change some things. The rule basically goes from your pre-image points of some x, y to some -1/5 of x and -1/5 of y. Basically divide your points by -5. That's what -1/5 means. So B prime will be this new point. Let's do this. Give me 1 second. I'm going to change this into blue because that's kind of what the original points were, and just make this one black. Okay, so B prime, we're going to divide this by -5 and this by -5, and these are all divisible by 5, which is good. So we'll get +1, +2. That'll be where B prime exists. C prime, divide those by -5 and we get 2, -3. And D prime, 0 over -5 is still 0, and 5 divided by -5 is -1. So let's plot those points, connect them, and we'll have the new object. So 1, 2 for B prime. C prime is at 2, -3. And D prime is at 0, -1. Now, Remember, this chapter is on similarity. Dilations are a way to begin creating similar objects without maybe knowing it first. Maybe you weren't aware what similarity was yet, and that's fine. But we just made something that was 5 times smaller and 5 times closer to the origin. The origin is your center of dilation. And I bring that up because this last problem had a center of dilation right here, right? And we could draw points to corresponding parts outward. This one's kind of interesting because it's negative, but I can draw from C to C prime and it goes through the origin here. You notice that? And B to B prime also goes through the origin, and D to D prime also goes through the origin. Probably less obvious. Whoops, that should be a vertical line. D to D prime also goes through the origin, like so. It kind of casts out the other way in a camera obscura effect kind of way. But it still does work, and if it didn't do that, then something went wrong, and this did not. All right, let's move forward. Lesson 8.2, similarity and transformations. This is where we start to maybe show that if we do this kind of thing, you'll be given 2 objects. If you do this reflection and this rotation and move it over here and then dilate it, then you can get the same object out so you know what corresponds. Let's fill in these blanks here. A dilation is a transformation that preserves blank but not blank. Well, dilation, what happens to all these things is the object stays similar. I know I'm saying a word before we're supposed to know it, but the object stays similar, and similarity means same shape, but not the same size. This is still a triangle, and it's still the triangle with the same obtuse angle here and all that kind of stuff. It preserves shape, but not size. Dilation, you can change that. You can also orient it in different ways. A similarity transformation is a dilation or a composition of blank and blank. Although we didn't purposefully do any rotation things here, this, for example, was a rotation of these objects, whereas this looks like it's just in a different place. Whereas you dilate, so you can dilate and translate and things like that. You can translate, rotate, you can reflect, and the object would stay congruent. It's only when you dilate that it actually changes its size. But you can have these other different transformations. They're called rigid motions. Rigid means it's firm, it's unchanging when it comes to its size. But then you can dilate on top of that. Dilations. You can dilate on top of that translation of that reflection and whatever. And then you have those objects. And I think this is really the point of why they have these things here. Not only are you practicing the transformation and on graphs, but you get this idea that, well, this is the part that corresponds. If you just move it that way, then you can see that they're the same way. So rigid motions, translations, reflections, rotations, those things are rigid. Dilations are not rigid because it changes the size, not the shape. Similar figures have the same blank, but not necessarily the same blank. They have the same, well, shape, but not size. Right? So it's the same thing as before. It's like the dilation thing. That's what's giving you the idea that these are really synonymous terms. See, dilations specifically have a center that you need to talk about. Similarity, not necessarily so. You can map parts onto it, but we don't really talk about that. Similarity transformations preserve blank measure only. We're talking angle measures. Or as opposed to congruent transformations, translations, reflections, rotations, they would also preserve side lengths. Like they would stay the same, but because similarity transformations, they have a dilation, it's not going to preserve that. Just the angle measures. A 60-degree angle stays as a 60-degree angle. It's not like when you have a scale factor of 2, suddenly it becomes 120 degrees. Congruence transformations, I just answered this. Congruence transformations preserve both side lengths, side lengths, and angle measure. Okay, so it's just some review of filling some things out so you're aware. More on 8.2? Yeah. Perform the similarity transformation. We graph triangle FGH with these vertices and its image after the following transformation. And they provide us a rule. It's like a dilation rule. Oh, and reflection in the x-axis. I totally missed that. So let's get FGH here. 1, 2 for F. 4, 4 for G. And H is at 2, 0. So pretty small guy. Looks like we're going to make it a little bigger after this. F, was this G? G and H. I'll let you go ahead and do the same. Da, 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 da. Ooh, that's okay. You okay with that being a little small? Not as thick as the other lines? Hopefully that's fine. Reflection in the x-axis. Now, the x-axis also, I'm not sure if you're aware of rules of these things. I often don't go off the rules, but this rule would be basically changing the y values, like here. Reflection in the x-axis means that this thing's going to flip over this line right here. I might change the color, like to red, just make it stand out, and make it different from my green that I'm going to have. So let's reflect over this line. That means it looks into a mirror, sees what's on the other side. So for example, I could make like an f prime that's 2 away from the x-axis over on this side. Call that f prime. G prime was at 4, 4. Now it will be at 4, negative 4. Oh, that might be 5. 4, negative 4. H prime is at 2, 0. It's going to stay at 2, 0, right? What's the opposite of 0? Still 0. That's not going to change. So it reflects in the x-axis. Hopefully you can understand that reflection for what we made of it. It's probably good that I have these thinned out like that. That's f prime, g prime, h prime. Let's do a second one, and I'll call it f double prime, g double prime, h double prime. Let's dilate this by doubling all these. Now keep in mind, what I just made was this. 1, negative 2, 4, negative 4, and this is still 2, 0. Now these are the ones we're going to double. Let's do this in purple. F double prime, let's double the x's, double the y's. Basically dilate, enlarge it with a scale factor of 2. 2, negative 4, 8, negative 8, and 4, 0. Not the biggest thing in the world. Whoops. 4, 0. Not the biggest triangle to fit within here, but let's do it. So 2, negative 4. That's f double prime. Remember, it's a dilation of the green, so it should grow out from the origin and double the length, and it's doing that. G double prime is at 8, negative 8. Is that negative 8? I think so. This is hard to tell. 1, 2, 3, 4. Yeah, I think so. Sorry if I missed slightly, but hopefully you get the idea of what you're doing if I'm counting it wrong. This is kind of small on my screen. H double prime is going to be at 4, 0, and I think I'm hitting it basically right there. I'm going to have to see it around the labels. So this guy, again, not drawn too thick, is that final triangle. And remember, it's a dilation of the green. There was a rigid transformation and reflection. We went from blue to purple with 2 transformations, a reflection over the x-axis and then the dilation. And remember, the dilation grows from the center, so everything was doubling in length, and it's double the size. All right, let's go to part B. Let's graph this one and do the same. Let's do 2 transformations. None of these include dilations, though. There's a translation and there's a rotation. So we will have congruent figures. We'll have congruent figures. They will not be similar. Well, they'll technically be similar, but they'll also be congruent. Let's take F, G. Oh, it's the same FGH. FGH. And let's do some... Let's make some magic. FGH. Let's make F prime, G prime, H prime by doing a translation first. Now, by the way, because translation is addition, subtraction, and all the other ones are changing signs or basically multiplication, either by negatives or whatever. If you translate first and rotate second, that's different from rotating first and translating second. All the other ones you can do one order or the other, just go first and second, but just letting you know. So we're going to translate these things. Let's figure out the translation points, x minus 2, y plus 1. Now, the 2 ways you can do it, you can either calculate it, 1 minus 2, and 2 plus 1. 4 minus 2 and 4 plus 1. And h minus 2 and, 2 minus 2 and 0 plus 1. You can either do that and then plot the points, and let's actually change that color. Whoops. Or you could understand the rule for what it is. And this rule is asking you to move all your points 2 to the left and 1 up. If you want to plot the points after that, that's fine. But I computed them, so I'll plot them from there. But you'll notice everything. Here's negative 1, 3 for f prime. Notice how that is 2 to the left and 1 up. This one will also be, let's just do that. 2 to the left, 1 up. And 2 to the left and 1 up. And you can see that those become the points that I also made. 2, 5, 0, 1. Those are all of those. And that is the translation of this thing. It's still a rigid motion, still a congruent figure. It just moved. It just moved. Now we're going to rotate 270 degrees clockwise, and I think it's worth mentioning that's the same thing as 90 degrees counterclockwise. I think I'd rather just go a 90 than a 270. Now, what I want to bring about here, and you can do this with your paper, I have a computer screen, but I'm going to show you a version of this. Whoa, I'm going to show you a big version of that. I'm going to show you a version of this where I'm copying and pasting it so I can actually manipulate this object. And for one, I'll show you why 270 and 90 degrees are the same thing if you go one direction versus the other, which you probably know that. If I go 270 degrees clockwise, that's 90, 180, 270. And by the way, I want you to focus on the green one, not the blue one. That's 270 degrees clockwise. Here's 90 degrees counterclockwise. 90. So you notice it's the same thing. You can do this with your paper. What I'm doing, because I'm not showing you a rule, so to speak, unless I'll show you the rule at the end if you want. But what I'm doing with this rotation, and again, focus on green only. What I'm doing with this rotation is figuring out where my objects are ending up ultimately if this was my new x-axis and my new y-axis. So basically, when I get g double prime, where is that point now? That's at -5, 2. You don't look at this like it's, to the side like that. Look at it like it's at its new place, -5, 2. When you see that point, you want to plot that as that's your rotation, -5, 2. This is g double prime after the rotation that we're doing. H double prime is at -1, 0. And F double prime is, I think that's -3, -1. Now, you would have to rotate your paper back and forth to do that. You might even write down the numbers before you plot them again. But hopefully you understand what I'm saying with that is you get to actually look, with the rotation, you get to actually look at where your points end up after the fact. Now, let's say that you learned rules for these things and you were aware of how this worked. 270 degrees clockwise is the same as 90 degrees counterclockwise. The rule for this would be you take your x, y values, and there's a little bit of swappage that goes on. You go from, I don't remember what they are, so I have to look at it for what it is. You would do y negative x. Y comma negative x. And what this means is whatever your values were, and I'll write them, I'll take these and do it for you and show you that they're the same thing. You take whatever y value you had and you put it as your new x coordinate. Don't treat this as a y. Treat this as the value that was y, and it's now your new x. So f double prime, see how it's -1, 3? Take the 3 and put it as your x coordinate. Oh, I did do something wrong then. Hold on. Must be -y. Must be -yx. Sorry. Let's do that again. Is that right? F. I think that's right. Okay. Take the y coordinate 3, make it your x, and change its sign. Sorry about that. Like I said, I don't memorize them. I just kind of look at the object and do what it does. And that's why I don't really use the rule. I use the paper rotation. Take the x value and make it your y, -1. Notice how f double prime is at -3, -1. -3, -1. G double prime. Take the y value, make it your x, and change its sign. Take the x value, make it your y. -5, 2. That's G double prime. And lastly, H double prime. Take your y, make it your x, change its sign. Take the x, make it your y. -1, 0. There's H double prime at -1, 0. Now I got it. Okay. Cool, cool, cool. So if you've ever dealt with rules like that, if you're given them, if you've memorized, I would not memorize these. I understand what it's doing, where it goes. I screwed up the first time, but I fixed it. And that is your final image. No dilations, so they're similar in a 1-to-1 ratio kind of way, but they're congruent. They're congruent. And we went from blue to green to purple. All right, nothing else on that page. Let's move forward. 8.3 on polygon similarity. This is where we really start to talk about actual similarity itself, not so much on graphs, but more so just the objects themselves. We do got to find points that correspond, though, because gone are primes. We're not talking about what's a prime versus what's not. We're doing more so what corresponds. Find the scale factor, angle congruence, and write the ratios of corresponding sides. Triangle JKL is similar to triangle PQR. Let me write that in this way so they're right next to each other. Doesn't matter that they're triangles, it just matters that we have the two figures with this letter order. 1, 2, 3, 1, 2, 3. J corresponds with P because they're both the first letter. Therefore, these two angles are congruent. K and Q are the second letters. They are congruent, and L and R are congruent as far as angles go. It's not the angles that matter so much, but now you see that this is nothing more than it's a dilation, but it's also a translation. That this is bottom left, things like that. That means this side corresponds to this side. They're not congruent, but they correspond when it comes to similarity ratio. And this corresponds to this, and this corresponds to that. No rotations or reflections needed. We know what goes where. Now, we are going from JKL to PQR. So when they say find the scale factor, understand that this is an enlargement. We're going from this to this. So scale factor, take any one of these value sets. It doesn't matter which one it's going to be. You can take 9 over 6, as long as they correspond, or 6 over 4, or 12 over 8. Any of these three will give you, when reduced, a fraction of 3 halves. And that is your scale factor. We tend to use K. Angle congruence, it looks like we're trying to write, this is both these. Angle congruence ratios of corresponding sides. Now, corresponding sides are based off these. I could have done that probably first. But angle congruence, I kind of already wrote it out. Angle J is congruent to angle P. Angle K is congruent to angle Q. And angle L is congruent to angle R. And I want to remind you that I did not really use the diagram to make that happen. I used the similarity statement. Sometimes you can use one, sometimes you can use the other. I gotta sneeze. Excuse me. Sometimes you can use one, sometimes you can use the other. I gotta drink water. But if you have the statement, you can use it without a drawing. Ratios of corresponding sides. I could also use the statement itself and do this. And I'm going to do it from the similarity ratio, from the large divided by the small, because it's an enlargement. This is my PQ over JK. And those are the first two letters. 1, 2 over 1, 2. QR over KL. QR over KL is the next set. And PR over JL. Letters 1, 3 and 1, 3. Now, once again, these aren't congruent sides. They correspond in such a way that when I divide those, they're all the same value. Okay. Number 2 for 8-3, solve for x. Once again, we see you can see it based on the angle. So they don't give us a similarity statement this time, but they give us by obviousness of the drawing, by markings of what's congruent, which parts are supposed to correspond. And this is, when it comes to solving for x, we're not all about what's enlargement versus what's reduction. It doesn't matter. There's so many ways you can set up this proportion, and you're not wrong. You can be wrong. As long as you go with corresponding parts in the same direction, you're not wrong. For example, x corresponds with 8, 9 corresponds with 6. I could write a proportion that says x over 8 equals 9 over 6. I went left to right, and left to right when it comes to the two things. I basically did the reduction version. I did parts that corresponded. That all worked out, and you're allowed to do that. I could also do this. I could do 8 over x equals 4 over 6. 8 over x equals 4 over 6. I went from right object to left object, corresponding parts, two different parts, and it worked out. I could also do this. 10 over 8 equals 15 over x. Now, I'm not saying whether this is recommended or not. Just if they ever ask for similarity ratio, this isn't it, because you're staying within the same object. But look at directionality. As long as they're oriented the same way, look at directionality. The left of the small divided by the bottom of the small equals the left of the big divided by the bottom of the big. That's something you can do. At any of these three sets, when you cross multiply and solve, and I'll do it for all three, and you can choose another set as long as you go the same direction. When I cross multiply and solve, I get x equals 12. I get x equals 12. And here, I get x equals 12, no matter what. Now, there are ways to do this correctly. There are ways to do this incorrectly. Let's do an incorrect version of this. Allow me to erase these, please. Let's do some simple ones that would be incorrect. X over 8 equals 10 over 15. What's wrong with that? We didn't go the same direction. X over 8 equals 10 over 15 didn't go the same direction. You went from big to small and small to big. Let's try this one. X over 10 equals 15 over 8. Mr. Robinson, they're the same direction. Yep, and they hit corresponding parts. Not their own corresponding parts. The bottom of the big is to the left of the small, as the left of the big is to the bottom of the small. I understand where you can hear sort of pattern stuff in it, but it's got to be bottom big, bottom small, left big, left small, like that. You can't cross those things up. They got to go to corresponding parts in some way, or at least be on the same part of it. So those are ways that you can mess it up. It's hard to mess it up once you know what you're doing with it. It's easier when they are oriented the same way. All right. Also part of number 2. If triangle BCD is similar to triangle GEF, find the length of BD. This is one of those ones where they're not oriented the same way this time, and sometimes it might help to draw them the same way. So I might take this small object, reorient to be exactly like this one. Notice how they say BCD is similar to GEF? B's got to be corresponding with G. Maybe I draw it this way. Let's draw a small version of this triangle. B is with G. C is with E, basically that right angle looking thing. If it is or not, I don't care. And D is with F. And now I can relabel these. From B to D is 2x minus 7. From B to C, oh, wait, there's no E in here. That should be a C. From B to C is x plus 4. Now this helps me see. Once again, you know what works now, right? This is like the top or the top right and the bottom. We know that these two correspond. We know that these two correspond. It helps us out there. Obviously, you can do it in different ways based on what you're looking at. Maybe the drawing is obvious enough for you, but this really helps me now. I can do something like 51 over x plus 4, blue, and now green, equals 57 over 2x minus 7. Now, what I didn't do, by the way, on this previous problem was I never did fraction reduction. I could have turned this into 3/2. I could have turned this into 2/3. I could have turned this into 5/4. I didn't. I don't know if I can reduce fractions on these things. I could divide both the top things by 3, but that's not something you might immediately recognize. So let's just go with it as it is. When you cross multiply here, I got to multiply 51 by all of 2x minus 7, and here, all of 57 by x plus 4. 51 times 2, we have to distribute now. 51 times 2x is 102. And minus 357. Wasn't prepared for big numbers. 57x, I hope I'm not messing up any of these as I go along. 228. Let me know. Let me know if I mess this one up. I'll figure it out. 45. 45, I'm subtracting 57 from both sides. So 45x equals... I'm not good at addition anymore. I used to be really good. 585. Okay, so that is 13. I think that's 13. Now, that's not the final answer. That's x. We have to find the length of BD. I hope that's right. We'll kind of double check this. BD is 2 times x minus 7. BD is 2 times 13 minus 7. 26 minus 7 is 19. And that's the length of that. Let's see if that actually all worked out. Let's say this is 19. Let's say that 13 plus that is 17, right? So they're saying 51 over 17. Let's see if this works. 51 over 17, which by the way is 3, equals 57 over 19, which by the way is 3. 3 equals 3. This checks out. And this is something we're going to be testing for later when we do things like side angle side similarity in section 8.5. But that checks out. Well, I don't know if it's going to be in the review, but that checks out. They're the same similarity ratio. So yes, it's good to double check and make sure that's all good. It's also good to answer the question being asked, which we did do. All right, let's go to the next page. We have trapezoids. RSTU is similar to ABCD. Same thing when it comes to letter order mattering and all that stuff. It doesn't just have to be for triangles, as we saw. Find the ratio of their perimeters. Ooh, even more to this. Okay. Find out what corresponds. RS is here and AB is up here. So these two correspond with each other. When it comes to, and I don't know if it matters what, like, I assume they're talking enlargement because the way that they show this thing. So let's consider enlargement. Let's say the scale factor is 24 over 18. and an enlargement, which is 4/3. Scale factor is 4/3. They didn't say find the perimeters. They said find the ratio of their perimeters. The ratio of their perimeters is equal to the similarity ratio, the scale factor, 4/3. I dubbed this thing R sub P. R sub P, the ratio of their perimeters, is equal to the scale factor. It is also 4/3. If we knew these lengths as whatever, then this would be 4/3 that size, 4/3 that size. Heck, 4/3 of 36 is 48, and this would be that. And if I add all these together and get the perimeter, you know how many times bigger it would be than this? 4/3 times bigger. So it would be exactly that, and that's all they're asking for there. Now, if they ask ratio of areas, it would be a different story. I don't yet see it here. Oh, we're going to talk about area there, so I'll let it be when it shows up, but that would be a different story. It wouldn't be 4/3. Number 4. Two similar triangles have a pair of corresponding sides of length 12 meters and 8 meters. They tell you what... Whoa. That's 10 and 3. Wait a second. I don't... Is this a different question? Let me read this. Two similar triangles have a pair of corresponding side lengths of 12 meters and 8 meters. The larger triangle has a perimeter of 200 meters and an area of 400 square meters. Find the perimeter and area of the smaller triangle. Don't forget units. Perimeter, smaller area. Okay. I don't see what this has to do with that problem. I'm going to say ignore this outright. Here's the thing. We have 10 and 3 as apparently corresponding parts. And 10 over 3 is not the same thing as 12 over 8, given that these are the corresponding things. So I'm going to wipe that out completely. I imagine it was probably part of a different question, which I do not see. It's not a part of these, so I'm going to... It's gone. Let's go with what they do have. You know what I will do? Let me just change this into a 12 and an 8. 12 meters, 8 meters. They did say triangles. Okay, those parts correspond. Two similar triangles have a pair of corresponding sides of length 12 and 8 meters. The larger triangle is a perimeter of 200 meters and an area of 400 square meters. Find the perimeter and area of the smaller triangle. So, you know, again, is it the longest side to have 200? No, it's not. Don't worry about that. They want to find the perimeter and area of the smaller triangle with everything that we know about this. Let's start with a similarity ratio. And let's go for a reduction this time. Let's go from big to small, 12 to 8. 8 over 12 is 2/3. So the similarity ratio is 2/3. Now, we have the perimeter of the larger triangle. What we just learned before is ratio of perimeter is the same as the similarity ratio. It'll also be 2/3. Now, 2/3 is small to big. So what we can do is set up a proportion that 2 is to 3 from any part, small triangle to big triangle, just as this unknown perimeter for the smaller triangle is to the perimeter of the larger triangle. The perimeter of the larger triangle is 200 meters. The smaller triangle will be 2/3 the size of 200. Ultimately, that's what we're doing. I don't even need to cross multiply. P is up on top. I can just multiply both sides by 200. P is 2/3 of 200. Now, this is not an exact value, like it's 400 thirds, which doesn't divide immediately by 3. There's an exact answer. If you want to round that, it's around 133.3 repeating, I guess. I'll just kind of put that because I really don't know what to put otherwise. My guess is maybe the 10 and the 3 were supposed to be used because that would be a clean number. I think you would get 60 meters. But I'm going with what it says on the 12 and the 8. I'm going to stick with that. Okay. Perimeter of smaller triangle, about 133.3 meters. We'll go with it. Area of the smaller triangle. The bigger triangle has an area of 400 square meters. Now, you do not do 2 to 3 and 400 in area. It's not 2/3 anymore. And in fact, this is also going to be another issue with values, I do believe. And if you want to see the 10 and the 3, I can set them up as well. You have to take the ratio of the areas. You take the similarity ratio or perimeter ratio, and you square it. Because you're taking 2/3 of 2 dimensions, x and y. 2 dimensions. It's 4/9. You don't use 2/3, you use 4/9. 4 is to 9. The area of the small triangle is 4/9 the size of the area of the big triangle. So Multiply both sides by 400. Area is 4/9 of 400, which is 1600 over 9, which is something. I'm going to use a calculator. I don't know. 1600 over 9. 177.7 repeating. This is square meters, by the way. 177.7 repeating square meters. Or, if I round it, 177.8. I won't box it. Okay. Now, that was if we were dealing with the 12 and the 8. Keep in mind, it did have the 10 and the 3, so I think those would have been whole numbers. So if you were curious, and if you're going to use that 10 meters and 3 meters, let me just kind of do that again as an alternative, because I don't know what you're going to use or have. So the similarity ratio, let's kind of look at as 3 to 10, and that can't reduce. So the perimeter ratio is also 3 to 10, but the area ratio would be 3/10 squared, which is 9 over 100, like that. Instead of being 30% of the size, it's 9% of the size of the other one. So for the perimeter, I'd say 3 is to 10, small to big, as the unknown perimeter is to 200. If you take 3/10 of 200, you do get what I said before, 60. 3/10 of 200, which is 60 meters. That's a little of a cleaner number. And then 9/100ths, squaring both of those, it's crazy, right? Divided by area over 400. We take 9/100ths of 400, 9% of 400, and you get 36. So 36 square meters, like that. So I'm guessing those were the answers they probably wanted to have when they set this up. I don't know where the 12 and 8 came from. So whether you're using one set or the other is kind of a, I don't know. Here's the 10 and the 3 as they were. I'm just playing with the worksheet as I see it. All right, let's move forward. Number 5. The polygons are similar. The area of one polygon is given. Find the area of the other polygon. So we get more practice on this. The similarity ratio, depending on how you want to write it, I can do 4 over 20, 4 inches over 20 inches for corresponding parts. That reduces to 1/5. The area ratio, we take that 1/5 and square it, and you get 1/25. And here's the thing, right? I think it's important to say why this happens. I mentioned the 2 dimensions thing. Here's the thing. We're taking these lengths, and I don't know if I can do this very well and just give it a good look overall, with this thing, but that 1/5 aspect says that each length is 1/5 the size of the other one. But what we're really asking ourselves right now is how many of these items can fit inside here? Look, 1, 2, 3, 4, 5. And then you got to go another thing up here. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. The point is it goes 2 dimensions. You can fit 25 of these inside one of those, not just 5 of them, right? You can fit 25 of them. So that's why that happens. All right, let's set up the proportion. 1 is to 25, as this unknown area for the small is to 100 for the big. Multiply both sides by 100, you get 100 over 25, which is 4. 4 square inches. And that is the area of the unknown of the other polygon. That's for that guy. So yeah, that's the idea is, and if you wanted to do this, look at this. Area of a rectangle, assuming it's a rectangle, is base times height. 20 times what is 100? 20 times 5 is 100. Well, the ratio is 1 to 5, right, for side lengths. So what's 1/5 of 5? 1. And what's 4 times 1? 4. So that's another way you could get it, or at least it validates what you did before, and it still works out. It's a good double-checking measure. All right, let's jump to this next one. Triangles. And, I'm not going to talk about areas for these things other than it's 1/2 base times height, but we don't have the height. You could get it. Maybe I should talk about it for a double check. Let's find the area of the smaller guy. Let's go with the larger version this time just to be different. Similarity ratio is 12 over 3, which is 4. You just got to know which way you went. 4 is 4 over 1. Let me even write that. The area ratio, whoops, The area ratio is 4 over 1 squared, which is 16 over 1. Which is a way of saying that this triangle, you can fit 16 of these triangles into this one. Whether or not it's drawn to scale is none of our concern. That is the point. So 16 over 1 similarity ratio as big, 96, is to unknown area here. Cross multiply, if you will. A times 16 and 1 times 96. Divide both sides by 16 and you get 6 square centimeters. So 6 square centimeters for the little guy right there. If you wanted a double check of that, 1/2 base times height is area of a triangle. So this one had to have been 16. Half of 16 is 8. 8 times 12 is 96. So if this thing has a 4-to-1 ratio of big to small, if this is a 16, then this must be 4 right here. Area of this triangle is 1/2, 3 times 4. 3 times 4 is 12. Half of that is 6. It still works out. We still get the same thing. So you could do it in the way of those other things, but the point is to know your area ratios and practice that, really. Okay. I don't even know how far along I am. I have no idea how long this thing is. Could be halfway done. This could be the last page. I do know how many sections there are, if it goes in that order. All right. If triangle AGM is similar to triangle KXD, find the value of X. So let's consider what kind of transformation this is. AGM looks like that. KXD looks like that. So it looks like just a little bit of a rotation, right? I got to kind of take KXD and kind of, just kind of go, like if I drew it right here, and I kind of do, I do endorse the redrawing thing if you think it helps you. I don't know. I can't even make it look similar, unfortunately. But this would be KXD, like that. So KX, X plus 3. It's weird when you have an X here and an X there, and they're totally unrelated. And D is X plus 6. So we know what corresponds. X plus 3 goes to 32, X plus 6 goes to 36. And let's do it. It's not unlike other problems that we did. I can say that much. Okay. X plus 3 is to 32, as X plus 6 is to 36. And by the way, let me do this differently. Let me do this instead. The reason I want to do it is to show that you can. You can do it. You can do it however you want, guys. I'm going this to this and that to that. The reason I'm really doing it is because I want to reduce this fraction. Now, there are other ways you could have reduced the 32 and the 36 the way that it looked, but when you see it as a fraction, I think you understand better when you can reduce. I can't do anything with this, by the way, guys. I can't turn 3/6 to 1/2. I can't cancel out x's. That's not a thing. That's not how it works. You have the pluses here. Stop it. Shut up. But you can reduce this. They have a common factor of 4, and that becomes 8/9. And I'd love to reduce when I can, or at least show you that you get the same answer as you're expecting. Cross multiply, even still, I get 9 times x plus 3 equals 8 times x plus 6. 9x plus 27 equals a lot better numbers. I don't want to do 32 times 6. Equals 8x plus 48. Subtract 8x from both sides, you get x. Subtract 27 from both sides, you get 21. And x is 21. Let's double check it. 21 plus 3 is 24. 21 plus 6 is 27. 24 over 32 is 3/4. 27 over 36 is 3/4. And it still works out. Number 7. If triangle BNV is similar to triangle BRG, BR is this whole length right here, 4x plus 7. Let's label it. BG is 18. Find the value of x. So they give you similarity, BNV, BRG. Sorry, we're not even close to drawing it how it is, but they're oriented the same way. You have a dilation only with a center of B, by the way. And let's totally just correspond those parts. Let's go. I can say 12 over 4x plus 7. This corresponds to that whole. Just as 8 corresponds with 18. Now, there are other kinds of ways we're going to do problems of this accord in section 8.6. But I would probably do this problem like this because of the way that's written. 8 over 18 I'd love to reduce, and I'm going to go ahead and do that before I keep moving forward. Divided by 2, you get 4/9. So 9 times 12 and 4 times 4x plus 7. I mean, the rest is algebra, so I'm going to kind of rush through that. 16x equals 80, therefore x equals 5, and that's all that was requested. It's always good to double check. 4 times 5 is 20, plus 7 is 27. 12 27ths is 4 ninths, and we saw 8 18ths was also 4 ninths, and that works. All right, lessons 8.4 and 8.5. I told my class that they seem to be the same. Angle angle is strictly 8.4, side side side, and side angle side is strictly 8.5, but we're proving triangle similarity. This is specific to triangles, these theorems, and triangles are very special in that way, and so it's not changing a lot of what we were doing before, unless we're trying to show that something's similar or say what we would have to do to indicate that it's for sure similar. So still use the concept of similarity, proportionality, all that when necessary. Determine whether the triangles are similar. If yes, state your reasoning and write a similarity statement. Okay. Now, this one here, again, they said write a similarity statement, so they didn't give one to us. And I wouldn't necessarily always go by obviousness of the drawing and say, this is clearly that, even if maybe it's drawn to scale. What you go by is the information or the nature of the diagram, like this one, which we'll talk about in a bit. Right here I have side lengths. Now, nothing is expected to be congruent. It's all about similarity. So what we do is we compare side lengths. I want to find the shortest side of this triangle and the shortest side of this triangle. The middle side and the middle side, or longest side, find the middle at the end. But those are the parts that, if they're similar, would correspond. Short to short, long to long, mid to mid. Otherwise, you couldn't double, right? I can't double the shortest side and bam, then it becomes the longest side of the other triangle and they're similar. It doesn't work like that. 22 and 16 are the shortest sides in this triangle, in these two triangles. 35 and 25 are the longest sides in these, and the mids are 20 and 20. This allows you to show what parts would correspond, and this is kind of a rotation, if you will, to make this right. But let's see if they all share a similarity ratio. Is 22 over 16, it doesn't matter which way you do it as long as you keep it the same, big to small. Is 22 over 16 the same as 28 over 20? And is it the same as 35 over 25? Now, as we try to answer the question, we'll then talk about what it means if it's true. 22 over 16 reduces, if I divide them, it's all about really trying to see if you can get down to the same reduced fraction. 11 over 8. Divide these by 4, and I get 7 over 5. Well, automatically that doesn't work. That being said, divide these by 7. Oh, that's a 25, excuse me. Divide these by 5, and you get 7 over 5 here. Okay, well, those are the same. Great. This is not. 22 over 16 is not. 11 over 8 is not the same 7/5. Not all in correspondence. Now, this is important because we learned that similar triangles have corresponding side lengths. Conversely, if you had all 3 side lengths in correspondence, you could guarantee yourself triangle similarity. If they're not in correspondence, and if you know they're not in correspondence, the triangles are not similar. Determine whether the triangles are similar. They're not. Don't bother with a similarity statement of saying triangle VWU is not similar to triangle MNL. They're not similar. There's nothing to correspond. You tested for correspondence. It didn't work. This would have been a side case, however, as if to say if all 3 sets of sides were in correspondence, yes, the triangles would be similar. It wasn't, so we move on. All right, this problem can get a little tricky because there are so many ways to do it, and there are so many ways to make mistakes. This might take a while to talk about, depending on how you want to talk about the problem. Let's start with a side test set. Let's go into this very, very cautiously. What are the 2 triangles? I'm going to redraw them. What are the 2 triangles that we see here? I see triangle PYX and triangle PRQ. I mention that because in a redraw, it is very important, especially as you learn section 8.6, and we're not talking about 8.6 right now, by the way. Especially as you learn section 8.6, you might be so inclined as to work off of split sides and assume that they're in correspondence with all the other sets of sides in both triangles, and that is just not true. I redrew that small one. Let's redraw the big one. Sorry that this is very not good looking. And I don't know if they're similar or not. I haven't tested. So this is 16. But what's PR? You got to add 5 and 15. Now this is the important part. you might have been inclined to set up a proportion. 15 over 5 equals this over this equals this over this. Oh, this is where you would have to be so careful. 5 and 8 are not, or 6, excuse me, 5 and 6 are not the whole side lengths of the bigger triangle. The bigger triangle is a side length of 15 plus 5 and 18 plus 6. Why does that matter? Because this one is the whole and the whole side lengths. And this is where you have to test for correspondence if you go by side, side, side. And I'm going to try it out. Hopefully it works, so then we could talk more about what to do next. 24 is 18, 15 and 20, and et cetera, et cetera. Let's try 24 over 18 equals 20 over 15 equals 16 over 12. And let's ask ourselves, is that true? Is that true? 24 over 18 reduces to 4/3. Divide them both by 6. 20 over 15 divided by 5, you get 4/3. Looking good. Divide these by 4, and you do get 4/3. That all checks out. Okay. So all three sets of sides, as far as what corresponds, are in proportion with one another. They share a similarity ratio of 4/3. Therefore, these two triangles are similar. I said out loud what they were, and when you get the redraw, I think it helps you even more. That triangle PYX is how I'll write that. PYX is similar to triangle PRQ. This is called the side-side-side similarity theorem. And I showed that. You have to demonstrate that that's true. It's like a proof without having the proof, right? So you have to demonstrate that, and I did. All three sets of sides are in proportion with each other. Now, as far as letter order, because we write our own similarity statement, it's our first one that we kind of did. Letter order doesn't matter for the first one you come up with. Generally, I would come up with it alphabetically. I just did it random this time. So PYX, as long as the other ones correspond. P does correspond with P, and R is with Y, and Q is with X, and that's why I did it in that way. Now, here's where I said you had to be careful. Make sure that you didn't put 5. I shouldn't have put, 15 over 5 equals 18 over 6. In some cases you can, but not for side, side, side. I wouldn't try 15 over 5 equals 18 over 6 equals, what did I do? 15 over 5, 18 over 6, and 12 over 16. I hope you can see a lot of what's wrong with that. No. Now, 15 over 5 equals 18 over 6. Those are both 3. But the 12 over 16, those parts don't correspond with what we did on those split sides. We don't do that. That's why the redraw of the whole and those comparisons was so crucial for the problem. Could have we done this another way? Yes, there's also side angle side. Now, side angle side is where you have two sets of sides that are in proportion with one another, and the included angle, the angle in between those sets of sides that you're testing with that are in correspondence, are congruent. Now, we did demonstrate that 15 over 20, I'll do it the other way. 15 over 20 equals 18 over 24. At least we demonstrated proportionality. Clearly now this is going to be the other way, but it still works, right? 3/4 equals 3/4. Now let's say you didn't have the 12 and 16. Would there be enough information without this 12 and 16 to show the triangles are similar? 2 sets of sides is not enough. If these were the diagrams you had, that's great that these are in proportion. This wouldn't be enough information. But the nature of the original diagram shows this angle P being shared in both triangles that are there. And any shared angle, meaning the exact same thing unto itself, is congruent to itself. When I say angle P is congruent to angle P, that sounds like a no-duh. But this is something known as the reflexive property. What it's saying is, when the drawings were separated, there's no way of knowing for sure, just by nature of the drawing, these two are congruent. Doesn't matter if it's called a P, because there are different ways we could, have that split. Maybe it's an angle bisector, yada yada. But when it's together, when we have this togetherness, we have that idea that it's a shared angle. It's the exact same thing, because it is literally the exact same thing. And this is the angle that's in between your two sets of corresponding sides. This is enough information. These two sets in proportion with one another, boom, 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 and the included angle congruent. These two triangles are similar. Once again, I could make let's make up a different one. Triangle XYP is similar to triangle QRP. QRP by side angle side. Similarity theorem. Two different ways we could prove it. And I did. And yeah, that's totally a different way to go about it. And that's a very common kind of drawing you're going to see. And it's likely we're going to see another kind of drawing pretty soon. Now, the thing that we're probably going to run across, if we run across these drawings again, you might get some instances where we start talking about congruent corresponding angles, such as this being congruent to this. They're corresponding angles like two parallel lines cut by a transversal and congruent, but not so fast because you never were told that these lines were parallel. Now that we know the triangles are similar, that's a case that you could make, but you weren't told the lines were parallel, so you could not use congruent corresponding angles. There's no way we could have used angle for this particular problem, and maybe we have more problems that we can do, but so far for number one, these two parts, no. Okay, I'm going to go ahead and move forward. I spoke a lot on this. I realize this is going to be a longer video as I'm teaching this kind of material. Oh my gosh, there are 4 more of this variety before we just hit number 2. I don't know how long this thing goes. Okay, this looks more like a case of angle. I know nothing about side lengths. I'm not saying whether it's right or wrong, but this looks like a case to test for angle. I know nothing about side lengths. I know angle measure sets. I know that angle Z is congruent to angle G. It's a given. All right angles are congruent. The right angle theorem, so that works out. Is angle X congruent to angle J? No, you see that angle measures clearly not congruent, but is angle X congruent to angle H? Is angle Y congruent to angle J? Remember, angle measures are preserved in similar triangles. Can we figure this out? Sure. Let's find out the measure of angle H. Let's see if it's the same as the measure of angle X. How do we find it? Well, this angle plus this angle plus this angle add to 180. Or take out the 90 completely. I don't need the 90. If you take 90 away from 180, then these two add to 90. Feel free, guys, add the 90 all you want. I'm going to give you the same answer here as I do there. The two non-right angles in a right triangle are complementary. They always add to 90 degrees because the third one's 90 and that makes it 180. So a little less work. Measure of angle H, therefore subtract 34 from both sides, you get 56 degrees. Cool. Here's the problem. That's not 61. That's not the same as the measure of angle X. The only case for this to have worked is similarity preserves angle measures, and one set of angles is congruent, as they're both 90-degree right angles. The other ones aren't. 56 ain't 61. Sorry, 61 ain't 56, 61 ain't 34. You can try all you want to try and get this to be 34. It's not going to be, because triangle angle, interior angle sums are always 180 degrees. That's why we can prove by angle, and we don't need angle. Because if 2 of the 3 angles in a triangle are congruent, then the third would have to be, because they always have to add to 180. This doesn't work. Angle H is not congruent to angle X. Congruent's not. Angle X, I don't think you have to go that deep into it, but not similar. I'm not going to make a similarity statement. I refuse. Not similarity. Not similar in this case here. No similarity statement to be had. No angle, even though that was my test. Let's go to this next one. It's the 4th one of the number 1 problems. This is a side angle side test for us. Now we could do side because they're right triangles. We could do Pythagorean theorem, find the third side. Pythagorean theorem. I'm not going to bother with that, not even as an alternative. Angle A is congruent to angle L given. By the way, not in this problem, but if this was a problem, I don't know what this answer is. Let's say it was 72. If there was a number here and we didn't know this one, and we might have to use Pythagorean theorem to find this one, because we got to find parts that not only correspond, but if we're going to do side angle side, we have to do the 2 sides that make the angle. So I'd have to know what these are anyway. Now, what corresponds? Short side of the short side, long side with long side. Do they share a similarity ratio? I hope for the sake of the test. Let's try it out. Does 48 over 44 equal 51 over 46.75? Now, I'll be honest, not going to bother with reducing fraction. This fraction's easy enough. That's 12 over 11. I don't want to bother with that one here. Let me just say what the calculation is. So 48 over 44, 12 over 11, if you will, is 1.090909, like that. Let's try 51 over 46.75. 1.090909. Yes, it's the same thing. I'll just say that we did reduce it. We found a way. 12 over 11 equals 12 over 11. And there is a way. I could multiply these by 3. I just didn't want to. And then reduce it. I didn't want to do that. So, angles are congruent. Two sets of sides are proportional, and they are the sides that make up the angles. So these triangles are similar. Let's write a statement. Triangle. Let's go alphabetical. ACN. That brings up bad memories of a pyramid scheme. I almost got caught up in. Triangle ACN is similar to, let's see, we go from the right angle across the shorter of the two known sides into the hypotenuse to do that, ACN. So let's go the right angle, L, across the shorter of the two sides is the hypotenuse, LVH. Triangle LVH. This is by the side angle side similarity theorem. So we've proven by side, 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 and side angle side in one problem. We missed angle, angle, boat here, and we got another side angle side. Let's hope we get an angle, angle somewhere over here. Not in this problem. This problem is very similar, no pun intended, very similar to the other one we did, except we don't know this third side length thing, so we can't do side, side, side. This will be another side angle side case for the very reason that we can say that angle n is congruent to itself by the reflexive property. And now we're going to do the test of these things. Now, although we're not in section 8.6, you know, that side splitter theorem, 40 over this is 32 over that, you could do that. Let's just go with actual full well knowledge of not only the section, but the fact that we're dealing in the two triangles. So I'm going to do 40 over 40 plus 12.5. 40 over 52.5, that's the whole length of this bottom side, equals 32 over 32 plus 10, 42. Are they the same? This time I'll try the fraction reduction. 32 over 42, I can divide them by 2, and I get 16 over 21. Let's see if we get 16 over 21 here. I'll start by doubling these, and I get, I'm doing this on the side, 80 over 105. And I can divide those by 5, and I get 16 over 21. Yes, so 16 over 21 here. Haha, that works out. So, and these are the sides that make up the angle. So the included angle, this will be a side angle side case. Similar by, thank you for giving us this side angle side, and they give us LMN in the big triangle, LMN. This corresponds in the same way, GHN for this one. That's a lot of green. And those are the finals. The last one for this problem set, I have parallel lines this time. This can be a confusing looking drawing for some people when it comes to how you can use those parallel lines to assist you. Let me thicken this out to emphasize something further. Look at the orange. They're marked parallel. Let's find transversals where we can come up with things that might help you. You want to do something where you make angles inside your triangle. For example, your triangles. For example, this could be a transversal right here, but I don't get something in both triangles with the transversal. Look, I have alternate interior angles that are congruent. Great. This one's not inside the triangle. I don't think that transversal is going to help you very much. You know which one will? This one. This transversal will help you plenty because you can come up with sets of angles that are congruent within the two triangles, like these. These are corresponding angles here. Corresponding angles in a triangle are congruent. When they're congruent, that helps you when it comes to things you want to do. So those are congruent. Those are corresponding angles, and that might help you better by seeing it that way. When I get rid of them, whoopsie. When I get rid of them, I hope you can still see them for what they were. Like that. Those angles are congruent. Now I'm going to write out what those angles are because I can't call it angle. I can call this angle J. I can't call this other one angle K. I need more. I need more. It's not just angle K because it might be this angle, 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 it might be the whole angle. You don't know which one it is. You got to use 3 letters like SKL. SKL. Why are these congruent? The corresponding angles theorem. Corresponding angles theorem says when lines are parallel, corresponding angles are congruent. They are corresponding angles, 2 parallel lines cut by that transversal. And I can't see any other sets of angles that I can show to be congruent with anything there. There's no other information to give me on that. Those are angles. Now I have these 2 triangles where I have this side and this side and this side and this side. And test correspondence with that. You can compare them by side lengths, but you can see clearly where they're going with 20 is to 32 as 14 is to 22.4. Is that true? I don't know. Let's find out. Is 20 over 32 the same as 14 over 22.4? Oh, divide these by 4 and you get 5/8. I know that number's 0.625, so I'm going to use this in the calculator and see if I get 0.625. 14 over 22.4. I get 0.625. Okay, so I'll say 5/8 equals 5/8. I'm just going to write the fraction version. It works. 0.625 equals 0.625. That one checks out. So side lengths are in proportion with each other. They are corresponding sides that have a known congruent angle that is made up by those two sets of sides. It's another side angle side case where these two triangles are similar. Triangle KLS is this one. So we got JKT for the other one. Triangle JKT, similar by the side angle side similarity theorem. Heck of a lot of those lately. Got to find an angle one of these days. All right, let's go to number 2, because all of those 6 problems were number 1. Find the value of x that makes triangle ABC similar to triangle DEF using side similarity. I've done this problem before. It looks awfully familiar to something I've done. So they're clearly oriented the same direction, which is good. I know that this corresponds to this, and this to this, and this to that. They're saying find the ones that make side similarity. Basically, these all would have to fall in proportion with each other. Now, I said it in the video that I know I've done this problem before. So I said in the video before that the x in this part is going to be the same x in this part. So I'm not required to use both sets of x's in some sort of way. I can totally just stick with one, and whatever I solve, I can use it for the other. So let me move myself. So for example, let's say I use the x minus 1 here with the 18 because they correspond. That's fine. And I could totally use this 4 and this 12 right here. There's nothing wrong with using that set and not using these x's at all. Or I could, and I don't know how long I want to spend on the problem. I know I've done this one. I just don't know what video it's on. It's something from the textbook, I think, though. It must be, because I did it in a video. So 4/12 is 1/3. Let's just jump into it this way. And multiply both sides by 18. Yeah, x minus 1 is 18 times 1/3, which is 6. X minus 1 is 6. Oh, you know where I did it? You know where this problem's from? It's from the textbook, but I think it's from one of the example sets. I don't think it's from the problem set. Yeah. Anyway, so I get x equals 7. Is that right? Without even doing a proportion with this one, let's plug it in and see. 7 minus 1, 3 times 7 plus 1. Let's do it the easy way. What's 12 divided by 4? 3. What's 18 divided by 6? 3. What's 24 divided by 8? 3. Yes, x equals 7. If I don't got to do a problem more than once, I won't. At least in teaching metric, especially if I've done it in some sort of way before. Writing, I don't think I've done proofs in the textbook we're here. Okay, writing proofs. Now, it's the same thing as we were doing. We just got to kind of spell it out. Given parallel lines prove they're similar, so we're going to either use angle, side, or side, angle, side. Given no markings of numbers, I assume it'll be an angle, one. And we know that it's true for what we do. They're saying prove it. They're saying it's true, just prove it to me. So, MN is parallel to JL. I imagine that should be also our first, I'm drawing arrows here. That should also be our first statement. Statement 1, segment MN is parallel to segment JL. Given. Now, I like to build off of a given statement before I do something else here, and I'm only going to do one set of these. With parallel lines, you can do, and I mentioned this before, you can do congruent corresponding angles, such as this N and this L, but I can't just call that N. You have to imagine that you're like inside that, it's not, you have to imagine you're not just inside the triangle right here, that it's the whole figure. So I can call it like KNM, something like that. Triangle KNM is congruent to angle L. An angle, that's fine to use one letter for that one. This is the corresponding angles theorem again. I'll spell it out because I have room. I've never had room in a proof to write. Normally I only have half the page, half the screen to work on. Now, I could do corresponding angles right here as well. There's no problem with that. I just don't want to repeat myself. I do want to go back to the reflexive property thing from before for diversity's sake. Angle K is congruent to itself. Let's go with that. Angle K is congruent to itself by the reflexive property of congruence. Something else I can probably also write in full. Reflexive property. Now I'm just stretching the time. And finally, the proving statement, right? So the proving statement, and it looks like those fit perfectly, triangle JKL is similar to triangle MKN. Why? JKL, MKN. Looks good. Two sets of corresponding angles that are congruent with each other. The angle similarity theorem. Done. Oops. Part B. FE is to DE as GE is to CE. There is a proportionality among two different sets of triangles. Now, something that I like to do, I don't know if it's accurate, so I apologize. You know when you say things are congruent, like this is congruent to that, which is not true. This is congruent to that, this is congruent to that. They use tick marks. What I like to do in these is use squiggly marks. FE is to DE. These segments, they're not similar to each other. Segments aren't similar. Objects, figures are similar. But they share the proportionality. I know which parts correspond to share the proportionality among other bits in the triangle. As GE, where's GE? GE is to CE. I'm showing which parts correspond. I'm giving myself the markings to make sure I know what's what. So I hope that that's okay that I'm putting that for you so you're well aware, especially because we don't have numbers. Because I don't know what the scale factor is. It looks like it's like 1.1. GE over CE, this is given. This is only a 3-step proof. Now, I got to prove similarity. I don't know anything about DC and FG. You can't assume they're similar, in proportion with the other ones. Let's go off angles. No parallel lines marked, nothing like that. We got this. Vertical angles. The angle E's, and I can't just call them angle E. Angle, I can call it like DEC. By the way, this looks totally like a reflection given how these parts correspond on top together and on bottom together. So I'll call this DEC, and then FEG is congruent to angle FEG. This is the vertical angles theorem. Vertical angles are always congruent. I think they should be capitalized, but that's okay. And the last one's the proving statement. So these two triangles, and it looks like they get the same letters. DEC is similar to triangle FEG. Why? That's a side angle side case right there. So hopefully you understand why I gave those things as well. It kind of helps show that. Now I really think I should capitalize this. Side angle side similarity theorem is the reason why. How many are there? C, probably one more. DE is parallel to GH. DE is right here. GH is right here. Prove the triangles are similar, DFE and GFH. Start with the given. Now this is going to be another angle case. You can't see anything else marked. This is another one of those where I will take step 1 into step 2. And I will build step 3 in a different way to be diverse. Step 2, before I mark it, I got 2 parallel lines cut by a transversal. You see that? Look at the purple, ignore everything else. I got alternate interior angles right here. I got alternate interior angles right there. Angle D and angle G are congruent to each other. They're alternate interior angles. I'm just going to do this alternate interior angle theorem. E and H are also alternate interior angles. They could also be marked as congruent. Absolutely. You should do that if you really feel compelled to. I'm going to go back to like another vertical angles thing. These angle Fs, if you will, EFD. And by the way, this one's more of a rotation. EFD is congruent to EFD. HFG. If you notice where these angles are, it clearly has to like rotate itself up over there. Not a reflection this time. Angle, what did I say? EFD and HFG. And that's not a requirement to do that then. It is a requirement in the similarity statement, which they made for us, by the way. So I hope they make it like a rotation, otherwise they messed up. But those are vertical angles, the vertical angle theorem. And lastly, we have the similarity statement here. Triangle DFE, this time I did not write it the same way as they did, is similar to triangle GFH. Let's first see if they did that right. DFE, GFH. Oh, one thing I should do is double arc mark those. There we go. So DFE, GFH, it goes from purple single to double dark blue, purple single, double dark blue. Yeah, that is the angle-angle similarity theorem. Okay. Done with proofs? No. How many more? This might be the last one here. All right. Given QS over TV equals RS over UV equals 3, so they tell you the similarity ratio, and QR equals 3TU, prove that triangle QRS is similar to triangle TUV. No angle things that are shown as far as congruency. The diagram is not going to allow us to use vertical angles, corresponding angles, reflexive property, alternate interior. A side-side-side case is going to be born here when you have all these proportions. Now, I will begin with the given Let's start with QS over TV equals RS over UV equals 3. Now, I don't know. There are 5 statements. I don't know if they want this to be its own statement. I kind of want it to be its own statement. If I need to draw a 6th thing, I will. So QR equals 3TU. That means 3 times TU, by the way. That's also given. Now, there's nothing I can really do with this, right? I'll keep them settled. What I do want to show is that this shares the same similarity ratio. Let's draw where these things are and see that it's making sense. QS is to TV as RS is to UV, as we want to see that QR is to TU with that same similarity ratio. So what we want to do is remember it's 3 times TU. Let's divide both sides by TU and get 3. Right? Divide both sides by TU. TU's gone over here and it divides from the QR and we get 3. That's just the division property of equality. I just divided that thing. Division property of equality. And I'm showing what now? That another part divided by its corresponding part is also 3. If these 2 sets divide to get 3 and this divides to get 3, then all of these must be in proportion with each other, as to say QS over TV equals RS over UV equals QR over TU. I'll even label it as such. Boom, 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 boom. Why? How can I justify this? Don't say side, side, side. That's not a similarity statement. It's a statement of proportionality. How did I say this? These equal 3. This equals 3. They equal each other. That's the transitive property of equality. Transitive property of equality. 2 things that equal the same thing are equal to each other. Now that statement will allow me to lead into my final, and that it looks like that they wanted this to be statement 2, because now I can fit this. My final statement of triangle QRS is similar to triangle TUV. Let's make sure that works. QRS, TUV. WXY. Side, side, side. Side, side, side. Similarity theorem. This shows that it will be side, side, side. Okay, I think that's the last proof on those. Let's do the last section. Maybe this is the last page or one more page. Lesson 8.6 on proportionality theorems. There are a few of them. There's the triangle proportionality theorem, which kind of looks like what's involved in the first 2. They called it the 3 parallel lines theorem. I call both of these sets also, by the way, the side splitter theorem. The side splitter theorem involved here, and by the way, they all have the same kind of thing in mind. And then there's another one on angle bisectors, which I'm sure will show up here. All right. They all kind of have the same sets. I'm not going to get too deep into the why of the matter. We're not proving them. Let's just kind of play with them. Solve for x. Now, what you saw before was we said something like this over this equals this over this. Like, because they're similar triangles. It totally worked out. It does, but it also works out in a way that you can work the split side of this, like this over this equals this over this. You can also do that. Provided that you're not doing this over this. And I showed you why before you couldn't do it, and we're not. But we can work it out this way. I can say something like 2x minus 5 over the split part of the big, x plus 8, equals 22.5 over the split part of the big 20. See that direct? There's more than one way you could do this, by the way. I could do this over that equals this over that. A lot of different ways you can set it up. Cross multiply, you'll be good. Now, I do want to reduce this. I can divide these both by 2.5. I naturally know that. It's 9 over 8, like that. I just like those numbers more. I'm sure you do too, but you're going to have to know to do that. You can solve it. I mean, after this, it's algebra. It's just the setup, geometrically speaking. So cross multiply, distribute. Subtract 9x from both sides, add 40 to both sides, and x equals, is that a clean number? No. Let's make sure that was correct in everything that I did there. That is 9 over 8. I'll double check and see that this works anyway. 8x, I might have made a boo-boo though. 16x minus 40, 9x plus 45, subtract 9x is 7, add that. Yeah, I think that's right. 85 over 7. Not clean. Not clean. And we're going to leave it like that. Let's make sure that, I'm going to make sure that's good. Make sure I didn't just screw something up when I was writing it. So 2 times, 8, oh boy, 2 times, I'm doing this in the background, you can't see this. Let me pause it and make sure to not waste your time. Okay, there's a mistake and I caught it before I even really finished double checking. This is x plus 8. I wrote x plus 5 here. So you probably caught it as well and you're yelling at the screen. So let's fix that into 72. Let's do that again. 112, and that works better. That should be 16. Right? I think so. Let's double check that one. Yeah, I didn't expect that to be right. Okay. 32 minus 5 is 27, and 16 plus 8 is 24. 27, yeah, that's 9/8. That works. Okay, cool. Sorry about that. All right, let's do this next one here. Now, as far as this, oh, by the way, the reason this thing works is because the triangles are similar. In the triangle, we're not doing a full proof. It's because these lines are parallel that this thing works the way that it does. That's what gets similar triangles. That's what lets this split sides, and we can do that. And same thing here, parallel lines. I probably should have brought that up first. Now we can do that same thing as before. Let's say that I said like 2x plus 8, say over 5x minus 4. That's fine. But I don't do 28 over 82 because 82 is the full length we have there. We got to figure out, what's 82 minus 28. Right, if you're going to work it out that way. Otherwise, you got to do this over the whole and do this plus this, which is not a problem, but just make sure we work it one way or the other. 82 minus 28 is 54, and I don't want to make a mistake on that one. 54. So 28 over 54. Now it's the parts that correspond in a way that work out for us. Definitely reduce that to x plus 8 over 5x minus 4. Equals, divide them by what? At least 2. 14 over 27, I think that's it. 14 over 27. Not much smaller. We have some work cut out for us. Cross multiply. And run out of room, why don't you? 54x plus... Sorry. 27 times 8. 216 equals 70x minus 56. Sorry about the room. Let's see what we got. Subtract 54x from both sides. I'm going to put it over here. I get 16x equals... I just hope the number's clean. Then I trust it. Equals 272. And x equals... 17. Oh yeah, 256. Yeah, 17. I'm going to trust it because it's a whole number. They did ask me to just solve for x, so I am done. All right, this next set is really no different when it comes to proportion idea. This over this equals this over this kind of thing totally applies. And 35 minus 20 is 15, and I can work it out that way. So just because it's split side, parallel lines need to be had, and they are. We're not going to give it to you without that if you're ever tested on something like that. So 15 over 20 equals, say, 4x minus 2 over 7x minus 11. And again, more than one way that you can write these proportions. I hope that you've learned that over the course of this hour 24 that I've done with you so far. This reduces to 3/4, much better kind of number than we had before, though we still have some work to do. Cross multiply, I get 3 times 7x minus 11 equals 4 times 4x minus 2. And let's rush through the algebra. 5x equals 25. X is 5. All right, and I get x equals 5. Please pause it if you want to do it for yourself and what have you. But it's that split side thing that still works out that way. All right, no change here. We got, oh, this is a different kind of question, though. I'll tell you, you'll see why. Number this. There's no number. X minus 3 over 35, sure, equals 4 over x minus 7. Got it? Yeah? That's true. X minus 3 over 35 equals 4 over x minus 7. Totally fine. Here's the problem. Not a problem, but here's the thing. You guys see it? That's 4 times 35, by the way. It's a quadratic. Now, I don't know what kinds of answers we'll get. I don't know if it's quadratic formula or what, but I'll tell you what. I'm going to give myself some room and see where we go from here. When you FOIL this and distribute it, you get x squared minus 10x plus 21. When you subtract 140 from both sides, as if to see if this does factor, that's going to be my first test, I get 119. And I know no factors of 119 other than 119 and 1. And for all intents and purposes, I'm going to assume that there's nothing that factors with. So let's do this. Let's subtract 21 over and get 119. And let's complete the square. 25 and 25. Oh, that does. Oh, hold on. Something does factor, because that'll be a perfect. I'm seeing things ahead. It's my knowledge of numbers. So that does factor. I don't know what it factors to. I just saw that would have given a perfect square. Though I could have kept solving that way, and I probably should be. (17 and 7). 17 and 7. 17 times 7 is 119. And negative 17 plus 7 is negative 10. There's the factorization. Okay, I didn't know. All right, so it's zero product property, x equals 17 or x equals negative 7. Now, what I got to check on is if I substitute 17 into x minus 3 and it's x minus 7, do I get positive numbers out? Yeah, 17 minus 3 is 14, 17 minus 7 is 10, and 14 over 35 equals 4/10. Negative 7, I would get negative 10 and negative 14. As much as those would work in proportion, because negative 10 over 35 is 4 over negative 14, you can't have negative lengths. So the quadratic was one wrinkle of it, and I also have an extraneous solution of negative 7 that does not work. Not because it was negative, it's because it gave me negative lengths when I substituted it in. So only x equals 17 works there. Now I could have solved by completing the square if I kept working, but I found out it was factorable, so I wanted to give you the factorization. Okay, this is the last page. Okay, I was like, I don't know how far we're going to go. And the last page, kind of the last two problems. If Km represents an angle bisector, solve for x. Now, this is another similarity of which I'm also not going to prove, but it's another proportionality thing that works in the whole, like, this over this equals this over this kind of thing, and a lot of different ways you can write it, but, or this over this equals this over this. And I say those out loud, assuming you've seen it before, and just, you start to naturally feel it for what it is. Only in an angle bisector does that work. Now, the whole thing is x, and I keep pointing out this length, so it looks like we're going to need that. If the whole thing is x and this is 12, you got to do x minus 12 to get that. And we're going to work that out. So I'm going to do 18 over 12 equals 30 over x minus 12. Cool. 18 over 12 reduces to 3/2. And I'm going to cross multiply and all that. So 3 times x minus 12 equals 2 times 30, it's 60. I get 3x equals 96 and x equals 32. If x was 32, then x minus 12 is 20. 18 over 12 is 3 halves. 30 over 20 is 3 halves. That does work out. That's the answer. And the last question, according to this thing here, is if triangle MNP is similar to triangle TSR, and NQ and SU are angle bisectors, find TS. Okay, so you're not going to... Okay, I got it. So you're not going to use... I'll probably restore those in a second. You're not going to use this thing that we like this over this equals this over this in that same way just because it's an angle bisector. It actually doesn't matter that they're angle bisectors that they're bringing up. What matters is their corresponding parts in similar triangles. So I'm not going to find out what this length is here and do something like this. And this proportion is as you probably would want to imagine it to be. The fact that the triangles are similar means corresponding side lengths are proportional. It doesn't matter what. They don't have to be side lengths of the sides of the object itself. They could be corresponding parts of any kind. It could be a certain diagonal that goes out another way, a certain altitude, a certain median, a certain angle bisector. If these are both, and notice the way that I drew these triangle things, this angle, I said M, N, P, and T, S, R. So notice the vertex of green is on the N and the S. And they did the angle bisector of both of those. So these are two angle bisectors of the same corresponding angles, which means these are corresponding lengths that follow the same order as this divided by, this divided by this is the same thing as this divided by this. That's how it works out. And that's what we're going to set up. 39 over 26, the angle bisectors of the corresponding parts of these two similar triangles, equals 5x minus 2 over 3x plus 1. And we can solve for x. And those do reduce. We can divide them by 13. And we get 3 over 2. Thank you. Cross multiply, 3 times 3x plus 1 equals, I'm sick of this kind of proportion algebra though. 5x minus 2, we get 9x plus 3 equals 10x minus 4. Subtract x from both sides, add 4 to both sides, we get x equals 7, and we're done. But they said find the length of TS. So if x equals 7, we're going to do 3 times 7 plus 1. Always answer the question being asked. And if there were some sort of units, we would use them. There aren't. 21 plus 1 is 22. That's the length of TS. All right, and I did see there was nothing else on the next page, so that will be it here. It seemed pretty comprehensive. And guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching here. We got just above the 90-minute mark. It was that one problem where I accidentally wrote x plus 5 instead of x plus 8. My bad. Womp womp. Do the review yourself. Check the timestamps down below if you want to find something else from here. Print out this PDF if you want to try and copy it down. You didn't do it the first time, or try it for yourself, and then go back and watch this thing. But thank you so much for watching. Next comes chapter 9, whenever that is, whatever it is. I assume trigonometry is going to come into play pretty soon here. So guys, take care. Thank you. I will see you in the next one. Bye-bye.